So this is number theory, lecture 14, halfway through the semester, which is always 14 weeks, 28 lectures. And keep in mind that we have 2 lectures this week on chapter 2. The last 2 sections we're covering on the Chinese remainder theorem and the Euler-Fermat theorem. Monday, a week from today, is review, and a week from Wednesday is our second exam. Any questions before we start about homework problems or anything in the lecture material? Any problems you'd like me to go over?
Professor, could you do on section 2.3, number 3?
Okay. Take a look.
Thank you.
So section 2.3, exercise 3. Suppose we let m equal 15. So what are the divisors of 15? 1, 3, 5, and 15. And if we calculate the Euler-Phi function for each of those numbers, phi of 1 is 1, 3 is a prime, so phi of 3 is 2, 5 is a prime, so phi of 5 is 4, and phi of 15 is phi of 3 times 5, because 3 times 5 is 15. And 3 and 15 are relatively prime, so this is phi of 3 times phi of 5. And phi of 3 is 2, and phi of 5 is 4. So this is 2 times 4, or 8. So if we take the sum over all the divisors of 15, phi of d, that's phi of 1 plus phi of 3 plus phi of 5 plus phi of 15. That's 1, 2, 4. 1 plus 2 plus 4 plus 8. And that's 15. So this is a special case of the theorem that if you sum over the divisors of a number m, phi of the divisor, you get the number m. And we want to do the same thing for 16, 17, and 18. So let me just do one more. Suppose we take m equal to 18. So what are the divisors of 18? So there's 1, 2, 3, not 4, not 5, but 6, not 7 or 8, but 9, and of course 18. And phi of 1 and phi of 2 are both equal to 1. Phi of 3 is 2. Phi of 6 is phi of 2 times 3, which is phi of 2 times phi of 3, which is 1 times 2, or 2. Phi of 9, so 9 is a prime squared, that's phi of 3 squared. So that's 9 times 1 minus a third, which is 9 minus 3, or 6. And phi of 18, 18 factors. It factors into 3 times 6, but 3 and 6 are not relatively prime. And if we want to use multiplicativity, we want to factor 18 into a product of 2 numbers that are relatively prime to each other, like 2 and 9. So phi of 18 is phi of 2 times 9. Phi of 2 times phi of 9. Phi of 2 is 1. Phi of 9 is 6. So if we sum over all the divisors of 18, phi of d, That's phi of 1 plus phi of 2 plus phi of 3 plus phi of 6 plus phi of 9 plus phi of 18. That's 1 plus 1 plus 2. Phi of 6 is 2. Phi of 9 is 6. And phi of 18 is 6. This is 1 and 1 is 2, 4, 6, 12. Lo and behold, it's 18 again, just what it's supposed to be. So that's how you do exercise 3. Any questions about that? No? Any other homework problems I should look at? Okay. So let's go to the Chinese remainder theorem. So all of these theorems are fundamental results in number theory.
Professor,
Yeah,
I'm sorry, my mic had an issue. Can you do number 7 from the same homework? I'm sorry.
2.3, number
2.3,
7.
number 7, yes, please.
Okay. So section 2.3, exercise 7. So we have Wilson's theorem, which I proved last week. It says that if P is prime, then P minus 1 factorial is congruent to minus 1 mod P. And we want to prove that the converse, basically, if P is not prime, then this isn't true. And it's actually even a stronger statement is what you have to prove. Prove that if M is composite and not 4, then M minus 1 factorial isn't congruent to minus 1 mod M. In fact, it's congruent to 0 mod M. So a proof can go as follows. Suppose we can write M is composite. So it factors into a product of two numbers, each bigger than 1. And suppose you can write M as A times B with A different from B. So you can write M as a product of two different numbers. Like, for example, 18 is 3 times 6. 3 and 6 are different. So, and let's say A is different from B, so one of them is less than the other. Let's say A is the smaller, and A is at least 2, and B is at most M minus 1. Because these are strictly between 1 and M. So M minus 1 factorial, this is all the product of all the numbers up to M minus 1. And when you're writing out all these numbers, you get to A, and then later you get to B up to M minus 1. And you can see M minus 1 factorial, it involves A and B. So this is some multiple AB times Q for some Q, which means it's congruent to 0 mod M. So you take a composite number, and if you can write it as a product of two factors that are different, this is true. Now, the only alternative is if this is not possible. So when is this not possible? So of course, if M is not a power of a prime, of one prime, then when you write m as, let's say, p1 to the k1, p2 to the k2 up to p sub r to the k sub r, p1 and p2 are different. I can write this as p1 to the k1 times all this. This is a product AB with A different from B. So if m is not a prime power, I can certainly factor it as a product of two different numbers. If m is p to the k and k is at least 3, then m is p times p to the k minus 1. And this is also a factorization into two numbers that are different. So if m is a prime power and the power is at least 3, I can factor it. So the only other case left is m equals p squared. And we know m is not 4, so p is not equal to 3. So if I look at m minus 1 factorial, this is 1 times 2 times 3. I have a p in there. I have a 2p in there, up to p squared minus 1 factorial. But p and 2p are different because p is different from 2, and 2p is not equal to m because p is bigger than 3. P is at least 3. So when I write m minus 1 factorial, I have at least two different factors of p. This is also p squared times some number, some integer q. For example, if p is equal to 3 and m is equal to 9, which is 3 squared, m minus 1 factorial is 8 factorial, is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. And I have a 3 and a 6. So this number is divisible by 18, so it's divisible by 9. This is 9 times something. And that's the proof. So again, you might have to go through this yourself at home and think about it, but this is the argument. Are there any questions?
No, Professor, thank you.
Any other problems I should go over?
Professor, from the same section, number 11, please.
Section 2.3, number 11. Oh, yeah, sorry, there's a typo there. Yes, thank you for pointing that out or for asking me about that problem. So section 2.3, exercise 11, we define the function f of n to be phi of n divided by n. And in general, if you take phi of p to the k, this is p to the k times 1 minus 1 over p. And if k is at least 2, this is not equal to p times 1 minus 1 over p, which is phi of p. So it's not true that phi of p to the k equals phi of p. What we want to prove is that f of p to the k equals f of p for all primes p and all positive integers k. So the proof goes as follows. F of p to the k is phi of p to the k over p to the k. phi of p to the k is p to the k times 1 minus 1 over p to the k. These cancel. This is 1 minus 1 over p, which is exactly phi of p over p, which is s of p. Yeah, so what's stated in the problem, there's just a typo. I should have said f of p to the k equals f of p. Yes. All right. Other problems to go over? Okay, so let's go to what is called the Chinese remainder theorem. So we know how to solve one linear congruence. You have the linear equation ax equals b. You learn in high school or junior high school how to solve this equation. But if you were in number theory and you want to solve this equation mod m, that is ax congruent to b mod m, this is solvable, has a solution if and only if b is congruent to 0 by modulo the greatest common divisor of a and m. And if b is congruent to 0 mod m, then the number of incongruent solutions, pairwise incongruent solutions x, is exactly this greatest common divisor of a and m. So this is a complete solution to the question of how you solve one linear equation. And in high school, after you solve one linear equation, you might try to solve simultaneous linear equations, and that can be interpreted in different ways with respect to congruences. But the simplest is the following. So this is the theorem. In the book, it's 2.9, Chinese remainder theorem. It says, suppose we have two moduli, m and n. So let m and n be positive integers. For all integers a and b, there's an integer x such that x is simultaneously congruent to a mod m and x is congruent to b mod n if and only if a and b are congruent to each other modulo the greatest common divisor of m and n. So for example, if you want to solve x congruent to 5 mod 7 and x congruent to 2 mod 3, can you find one number x which satisfies these two congruences simultaneously? So in this case, what are your moduli? M is 7, n is 3, a is 5, b is 2, And what is the greatest common divisor of m and n? That's the greatest common divisor of 7 and 3, which is 1. So A is congruent to B. Mod 1, every number is congruent to every other number, while mod 1, because 1 divides every integer. So this has a solution. And if you wanted to try to find it, you could say, well, x is congruent to 5 mod 7. That means x is 5 plus 7 times y. Any number that's congruent to 5 mod 7 is of this form. And this x is also congruent to 2 mod 3. That's the same as saying 7y is congruent to 2 minus 5, or minus 3 mod 3. Of course, this is a very easy problem because 3 is 0. So if and only if y is congruent to 0 mod 3. And if you take y equals 0, x equal 5 is a solution. Well, that was really easy because 5 is congruent to 5 mod 7, and 5 is congruent to 2 mod 3. So this is not a proof of anything. This is just an example of applying the Chinese remainder theorem. But the method of solving the problem actually gives us a pretty good hint about how to prove the theorem. So let's prove the Chinese remainder theorem. So x congruent to A mod m means x has to be a number of the form a plus my for some integer y. And x is congruent to B mod n if and only if a plus my, because every x is of this form, if you can find a y such that a plus my is congruent to B mod n, which is the same as saying m times y is congruent to B minus a mod n. And by our theorem about linear congruences, we can solve this linear congruence. That means we can find a y that satisfies this congruence if and only if B minus a is congruent to 0 modulo the greatest common divisor of m and n. And this is the same as saying a is congruent to b modulo the greatest common divisor of m and n. And we can, in fact, find all solutions to our pair of congruences. So let x and y be two solutions of the congruences. So we have two solutions. So x is congruent to a mod m, and x is congruent to b mod n. And also, y is congruent to a mod m, and y is congruent to b mod n. So we have two solutions. But of course, if x is congruent to a and y is congruent to a, this means x is congruent to y mod m. And if x is congruent to b and b is congruent to y, x is also congruent to y mod n. So this means m divides x minus y, n divides x minus y. So x minus y is a common multiple of m and n. And so the least common multiple of m and n divides x minus y, or x is congruent to y, modulo this least common multiple. So let me repeat this additional part of what will be the Chinese remainder theorem. So I just proved that if you have two congruences, x congruent to a mod m and x congruent to b mod n, there exists a number x that satisfies both congruences simultaneously, precisely when a is congruent to b, modulo the greatest common divisor of m and n. So let's suppose that happens, and we know there's a solution, and I want to find all solutions. So suppose y is another solution of these two congruences. So this says that x is congruent to y mod m, x is congruent to y mod n. This means m and n both divide x minus y. So x minus y is a multiple of m, and x minus y is a multiple of n. So x minus y is a common multiple of m and n. And every common multiple of two numbers is divisible by the least common multiple of those numbers. So LMN in square brackets, this is the least common multiple, divides x minus y. So if x and y are two solutions, then x is congruent to y mod m. And let's suppose the converse. Suppose x is congruent to y modulo the least common multiple of m and n. So x minus y is this least common multiple times something. So, so suppose x is congruent to a mod m, and also x is congruent to b mod n. But x is equal to y plus this least common multiple times q. So I can replace x by this, y plus this least common multiple of m and n q is congruent to a mod m, and y plus this least common multiple q is congruent to b mod n. But this is divisible by m, so this is 0 mod m. So y is congruent to a mod m because the least common multiple of mn times q is congruent to 0 mod m, because this is a multiple of m. And similarly, y is congruent to b mod n. So this is the second part of the Chinese remainder theorem. If x congruent to a mod m X congruent to B mod n has a solution, then Y is also a solution. If and only if Y is congruent to X modulo the least common multiple of M and N. So there are an infinite number of solutions and they all lie in one congruence class. So let me work out another example of the Chinese remainder theorem. Suppose I have the system of congruences X congruent to 5 mod 21 and X congruent to 19 mod 56. So the greatest common divisor of the two moduli, 21 and 56, 21 is 3 times 7, 56 is 8 times 7. The greatest common divisor is 7, and 5 is congruent to 19 mod 7. So this system of congruences has a solution. And to find it, I can do the following. X congruent to 5 mod 21 means X is an integer of the form 5 plus 21y. And that's going to be congruent to 19 mod 56 if and only if 21y is congruent to 19 minus 5 or 14 mod 56. Everything here is divisible by 7. This is the same as dividing by 7. 3y congruent to 2 mod 8. What's the solution of this congruence? I think y equals 6 is the solution, because 3 times 6 is 18, minus 2 is 16, is 8 times 2. And this is going to have a unique solution if and only if y is congruent to 6 mod 8, which means y is equal to 6 plus 8z for some integer z. And so x, which is 5 plus 21y, is 5 plus 21 times 6 plus 8z. This is 5 plus 126 plus 21 times 8, which is 168 z. Which is 131 plus 168z. Notice that for 21 and 56, the least common multiple of 21 and 56 has to be divisible by 3 times 7 times 8, which is 168. So the set of all solutions of the system of congruences, this is all x congruent to 131 mod 168. Let's just check. 131 is congruent to 5 mod 21. 131 minus 5 is 126. That's exactly 21 times 6. So 131 minus 5 is divisible by 21. And 131 is congruent to 19 mod 56. That means 131 minus 19, which is 112. That's 56 times 2. So 56 divides this. So 131 really is a solution of this system of congruences. And the set of all solutions is all numbers congruent to 131 modulo 168. So this tells us when we can solve two simple congruences with respect to different moduli. And suppose we have more than two. So this is a more general version of the Chinese remainder theorem. Theorem 210. So this says let k be at least two, a1 up to a sub k integers. And I want moduli m1 up to m sub k pairwise relatively prime. Positive integers. So consider the system of congruences x congruent to a1 mod m1, x congruent to a2 mod m2, x congruent to a3 mod m3. I have k of them, x congruent to a sub k mod m sub k. So if the moduli are pairwise relatively prime, this system of congruences has a solution. So if you have pairwise relatively prime moduli, you can solve these k congruences simultaneously. Moreover, the integer y is a solution if and only if x is congruent to y modulo the product of all these moduli. So if you only have two congruences, if k equals 2, this is just a special case of the Chinese remainder theorem, because m1 and m2 are relatively prime, so a1 is congruent to a2 mod 1, and the least common multiple of m1, m2 is just the product m1 times m2. So the proof is by induction on k. And for k equal 2, this is just a special case of the Chinese remainder theorem I just proved. So to prove this by induction, let k be any number at least 3 and assume the statement is true whenever you have k minus 1 congruences. So let's see, the k minus first congruence will be x congruent to a sub k minus 1 mod m sub k minus 1. So because this is true for k minus 1, we have, so by the induction hypothesis, there exists an integer x such that x is congruent to ai mod m sub I for the first k minus 1 congruences. I don't know anything about the last congruence yet, but for the first k minus 1, I can have an x that satisfies these k minus 1 congruences. But because the integers are pairwise, the moduli are pairwise relatively prime, if I take the product of the first k minus 1 moduli and the last, these two integers are relatively prime. So see, so where I said by the induction hypothesis there's a solution, let me call that solution Z. So Z is a solution of the first k minus 1 congruences. Now, by the Chinese remainder theorem, in the case k equal 2, there exists in x an integer such that x is congruent to z modulo m1, m2 up to m sub k minus 1, and x is congruent to a sub k modulo m sub k. Because these moduli are pairwise relatively prime. And if x is congruent to z, mod m1 up to m sub k minus 1, that means x is congruent to z modulo any one of these smaller factors, mi for all I from 1 up to k minus 1, but z is congruent to a sub I mod m sub I. So we now found a solution to all k congruences. X is congruent to ak mod mk, and x is also congruent to ai mod mi for I going from 1 up to k minus 1. And if y is another solution to all of the k congruences, then y is congruent to ai is congruent to x mod mi for all I, and so mi divides y minus x for all I. But because these moduli m sub I are pairwise relatively prime, their product divides y minus x. Or in other words, x is congruent to y modulo m1 up to m sub k. So if you have one solution to the k congruences, then there's exactly this one congruence class, which consists of all solutions of the congruences. So that is the proof. I mean, it's all written down legibly in the book, and it takes some thinking, of course, but any questions about this? Let me look at an example. So here's an example, which is very pretty. It's in the book. Suppose we have four congruences, x congruent to 2, mod 3, x congruent to 3, mod 5, x congruent to 5, mod 7, and x congruent to 7, mod 11. So the A1, 2, 3, and 4 are 2, 3, 5, and 7, and the moduli 3, 5, 7, and 11. So notice that 3, 5, 7, 11 are pairwise relatively prime. So the system has a solution, and the set of all solutions is everything has a solution x. And if you take one number x, the set of all solutions is, so, and y is a solution. If and only if y is congruent to x, modulo the product of the moduli, 3 times 5 times 7 times 11. Or y is congruent to x, modulo 1155. So let's find the solution. So let's just do it step by step. First of all, find x such that x is congruent to 2 mod 3 and x is congruent to 3 mod 5. So I'll let you do that. Find a number x which satisfies these two congruences. Right? Can someone give me a solution?
I could be wrong, maybe 8?
Well, 8 minus 2 is 6, is divisible by 3. 8 minus 3 is 5, is divisible by 5. So this is all x congruent to 8 modulo any, so x equal 8 works, and anything congruent to 8 modulo 15. So that's for the first two congruences. Now, if we also want to solve the third, we want to find an x which is congruent to 8 mod 15 and congruent to 5 mod 7. So what's the solution of this system of congruences? Whatever it is, will be unique modulo 15 times 7, which is 105. So what is it? What's the number congruent to 8 mod 15 and 5 mod 7? This is a little bit harder. Is there a solution? Well, we know there's a solution because the moduli are relatively prime. Let's see. We can say that x is congruent to 8 mod 15 means x is going to be equal to 8
Yeah,
plus
68.
15 times some number y. And that's going to be congruent to 5 mod 7. That's the same as 15y is congruent to minus 3 mod 7. Of course, mod 7, 15 is the same as 1. So y is congruent to minus 3, or if you like positive numbers, y is any number which is 4 mod 7. And if you let y equal 4, x will be 18 plus 15 times 4 is 8 plus 60 is 68. And let's just check. If you let x equal 68, 68 minus 8 is 60, is 15 times 4. 68 minus 5 is 63, which is 7 times 9. So x congruent to 68 mod 105 satisfies the first three congruences. But we now have to figure out the last congruence as well. So we want to find the number x such that x is congruent to 68 mod 105, and x is also congruent to 7 mod 11. So this will be some unique congruence class modulo 11 times 105, which is 1,155. So what's the solution of these two congruences? So x is congruent to 68 mod 105 means x is 68 plus 105 times some number, I'll call it t. And that has to be congruent to 7 mod 11, which means 105t is congruent to 7 minus 68, which is minus 61 mod 11. And minus 61 is congruent to 5 mod 11. And 105 mod 11 is, let's see, 105 is congruent to minus 5. Right? 105 is congruent to minus 5 mod 11 because 105 minus 5 is 110 is 11 times 10. So 105 is the same as minus 5 mod 11. Minus 61 is the same as 5, which means t is congruent to minus 1 or 10 mod 11. So x is 68 plus 105 times 10, which is 1050 plus 68, which if I've done my arithmetic right, you never know, is 1118. So I claim that x equals 1118 is a solution of the four congruences. These were the four congruences. So let's just check. 1118 minus 2 is 1116. Is that divisible by 3? This is 3 times 3, 72. So this is congruent to 0 mod 3. 1,118 minus 3 is 1,115, which is certainly divisible by 5. It's 5 times 253, I think. Is that right? 2, 5 into 11 is 2, 523. What about, is this number congruent to 5? 1,118 minus 5 is 1,113. But I divide this by 7, I get 1. 41, 7 into 41 is 5. 63 divided by 7, 9. So 7 times 159. So x 111, 1,118 is congruent to 5 mod 7. And what about 11? 1,108 minus 11 is 1,107. All right.
Maybe minus 7,
Oh,
not
thank you.
minus 11.
That's a lot better. 1,118 minus 7 is 1,111. And I think that's exactly 11 times 101. So this number solves all 4 of my congruences. That's kind of nice. Now, there's a important application of the Chinese remainder theorem to solving polynomials, right? I mean, you remember in school, you solve equations like, you know, x squared, you solve equations like this, right? Solve a quadratic equation. Now, for us, we want to solve, so to call this some polynomial f of x. This is what you do in high school. You solve equations. But in number theory, we might want to solve this modulo m. Just look at this as a congruence. For example, in high school, if you had to solve f of x equals x squared plus 1 equals 0, that has no solution. A square is never negative. But if you wanted to solve f of x equals x squared plus 1 congruent to 0, modulo 13, this might have a solution. Actually, that's interesting. So can you see whether you can solve this? You can't solve this in the integers or the fractionals or the real numbers. But what about solving this as a congruence? Can you find a number x such that x squared is congruent to minus 1 mod 13? Right? It's the same thing. Can anyone find a solution or prove there is none?
5.
Yeah, well, if you let x equal 5, 5 squared is 25 is congruent to -1 mod 13 because 25 minus -1 is 26, which is 13 times 2. And what about -5? Now, of course, mod 13 minus 5 is the same as 8. Let's try 8 squared minus -1. That's 64 plus 1 is 65, is 13 times 5. So in fact, this has solutions x congruent to either 5 or 8 mod 13. So solving polynomials and congruences is somewhat more interesting than solving it in the reals often. This would have no real solution, but it has mod 13, 2 whole congruence classes of solutions. And it really is true. If x is congruent to 8 mod 13, suppose that x equal 8 plus 13, which is 21. So this should also be a solution. Let's see. What is 21 squared? So if you take 21 times 21, that's 441. And 441 minus -1 is 442. Is that divisible by 13? I don't know. 39, 50, this is equal to 13 times 34. So 21 squared is congruent to -1 mod 13. Really very interesting. So we can use the Chinese remainder theorem to at least reducing. So suppose that f of x be a polynomial. With integer coefficients. Like x squared plus 1. And suppose we have m, a modulus, and I can write it as a product of prime powers, p1 to the r1, p2 to the r2, up to p sub k to the r sub k. So we can say that f of x has a solution mod m if and only if f of x has a solution modulo just this prime power, pi to the ri, for all I going from 1 up to k. It doesn't mean that these have the same solution, but they have, each of these congruences has a separate solution. So the proof, this is a theorem. So suppose for each of these prime powers, f of ai is congruent to 0 mod pi to the ri for I going from 1 up to k. So these are different numbers. But then by the Chinese remainder theorem, there exists an integer a, which is congruent to ai mod pi to the ri for all I from 1 up to k. Because these moduli are distinct prime powers. They're pairwise relatively prime. So if a is congruent to ai mod pi to the ri, that means f of a is congruent to f of ai. It's congruent to 0 mod pi to the ri. So f of a is congruent to 0 modulo the product of these prime powers. Or f of a is congruent to 0 mod m, because m is this product. So everything becomes clearer when you see an example. So let me take an example from the book. It's a quadratic equation. Suppose we want to solve f of x equal x squared minus 34, congruent to 0 modulo 495. So it's enough to factor 495 and see if we can satisfy this congruence for all of the prime powers that divide 495. So 495 is certainly divisible by 5. Let's see, it's 5 times 100 is 500. So 5 times 99 will be 495. And 99 is 9 times 11, or 3 squared times 5 times 11. So it suffices. So there are 3 prime powers that go into this. So it suffices to solve independently x squared minus 34 congruent to 0 modulo 9. This is just 9. X squared minus 34 congruent to 0 mod 5, and x squared minus 34 congruent to 0 mod 11. Of course, 34 is the same as minus 2 mod 9. So this is the same as x squared plus 2 congruent to 0 mod 9. Minus 34 is 1 mod 5. This is the same as x squared plus 1. 34 is minus 1, so minus 34 is plus 1. X squared plus 1 congruent to 0 mod 5. And 34 is the same as 1 mod 11. X squared minus 1 congruent to 0 mod 11. So this congruence is the same as this. This congruence is the same as this. This congruence is the same as this. What's the solution of x squared plus 2 congruent to 0 mod 9? Let's see, if I take x equal to 5, this is 25 plus 2 is 27 is 0 mod 9. So we have that x squared plus 2 congruent to 0 mod 9, if and only if x is congruent to 5 mod 9. X squared plus 1 is congruent to 0 mod 5. Let's see, 4 plus 1 is 5. So if I take x equal to 2, x congruent to 2 mod 5. X squared minus 1 congruent to 0 mod 11. So x squared is congruent to 1 mod 11. Let's see, what are the squares? What are the squares? 1? Well, yeah, I could just take x equal to 1. X squared minus 1 is congruent to 0 mod 11, if and only if x is congruent to 1 mod 11. So I can solve these congruences modulo prime powers if I can solve these congruences, and I can solve each one of them. And what I have to do is to find a single number a which satisfies these congruences simultaneously. I have to find a number a which satisfies all of these. And one solution is a equal to 122. I just worked that out. I mean, it takes a while, but you take a piece of paper and give yourself some time. You can work it out. Let's just check. 122 minus 5 is 117 is 9 times 13. 122 minus 2 is 120 is 5 times 24. 122 minus 1 is 121 is 11 times 11. So A equals 122 is the solution. And so we have that x squared minus 34 is congruent to 0 modulo 495 if and only if x is congruent to 122 mod 495. So I solved this polynomial equation mod 495 by factoring 495 into a product of prime powers, solving this for each of the prime powers separately, using the Chinese remainder theorem to find a simultaneous solution of these three congruences. That gives me this, and I've solved the problem. Okay, let me just do one more example of an application of the Chinese remainder theorem. So the Chinese remainder theorem satisfies very simple congruences. But suppose we have something slightly more complicated. I'll just make up something and see what happens. Let's say 3x congruent to 7 mod 11 and 2x congruent to minus 1 mod 5. So how can I find a simultaneous solution of these two congruences? So what I can do is say that I can solve each of these congruences separately. So what are the solutions of 3x congruent to 7 mod 11? So there's going to be a unique solution mod 11. And what is the solution going to be? Find a solution to this congruence. All right, can anyone find a solution? I mean, if nothing else, you can just start going through the numbers. 0, 1, 2, 3, 4, up to 10. And you'll find this. And we know by the Chinese remainder theorem, because 3 and 11 are relatively prime, this will have a unique solution mod 11. Any suggestions?
Six.
6, yeah. Because 3 times 6 is 18. 18 minus 7 is 11. And what about a solution to 2x congruent to minus 1 mod 5? This will also have a unique solution mod 5. So what's the solution of this congruence?
Two.
2, because 4 plus 1 is 5. So 3x is congruent to 7 mod 11 if x is congruent to 6 mod 11. And 2x is congruent to minus 1 mod 5 if x is congruent to 2 mod 5. And if I can solve these two congruences, and this is exactly in the form of the Chinese remainder theorem, any x that solves both of these congruences will solve both of these. And this will have a unique solution modulo the least common multiple of 11 and 5, which is 55. So can anyone find a solution, a simultaneous solution of these two congruences?
$17.
17, yeah. Because 17 minus 6 is 11. 17 minus 2 is 15, which is 3 times 5. So any x congruent to 17 mod 55 should be a solution of the original problem. So let's check. 3 times 17 is 51. So 3 times 17 minus 7 is 51 minus 7 is 44, which is divisible by 11. And 2 times 17 minus 1 is 34 plus 1 is 35, is 5 times 7. So 17 is the solution of those two linear equations. So we reduce each of these to simple equations where the coefficient of x is 1. We use the Chinese remainder theorem and we solve the problem. Okay, so this is the Chinese remainder theorem, and it's very important. And on Wednesday, I will prove the Euler-Fermat theorem, which is also very important. And then we'll review for a week and have the second exam a week from Wednesday. Okay. Also, this week I'm having office hours Monday, Tuesday, Wednesday, and Thursday. And I have them at 2 different times during the day and twice in the evening. So it gives people a chance, if you work during the day or if you're busy at night and you can come during the day, there's a lot of opportunities just to come online and ask questions if you have anything you would like me to explain or any problems you would like me to solve. Okay. Any questions before we go? Okay, everyone. See you or talk to you later in the week. Bye all.
Thank you, Professor.
Have a good day, Professor.
All right, bye all.